Welcome back. This is COT 3100. Today's topic is about primes and greatest common divisors. However, in this section, we are going to look at just a few topics that is our interest, and then we will go over in the next class. We will go over the next chapter, few topics in next chapter, which is chapter 5, and then we will look at some topics in chapter 6 that are our interest, and we may even include some short discussions about the probabilities at the very end of the very last lectures. So let's take a look at the primes and greatest common divisors. So we're going to look at the prime numbers and their properties, and also we want to look at the greatest common divisors and the least common multipliers, what it means and why is it important. The application of the prime numbers, there are numerous applications for prime numbers, especially in computer science field, and also we use them in coming up with the algorithms for the security, encryption, decryption, and a lot of applications that requires the knowledge of prime numbers and what they are, what they mean. So let's take a look at the primes. A positive integer p greater than 1 is called prime if the only positive factors of p are 1 and p itself. And gonna bring up the document camera. I want to write some of the stuff down to make sure that we are clear in this topic. You're saying any integer p that is greater than 1, all right? That is divisible by 1, and p itself, it is called prime number. Let's take a look at this an example. Example would be greater than 1, let's say 2. What numbers 2 are divisible? 2 is divisible by 1 and also by itself. How about 3? 3 is divisible by 1 and itself. And how about 4? 4 is divisible by 1, 2, and itself. And 5, it's only divisible by 1 and itself. 6 is divisible by 1, 2, 3, 6. 7 is divisible by 1 and 7. 8 is divisible by 1, by 2, by 4, and by itself. 9 is divisible by 1, by 3, and by itself. All right? Just here, if there is any integer that is divisible by 1 and itself, it's called prime number. But look at here, this one is a prime, this one is a prime, this one is not a prime number, this one is a prime, this one is not a prime number, this one is a prime, this one is not a prime number, and this one is not a prime number. So we see 2, 3, 5, and 7 among the integers between 0 and 10 are prime numbers. Those numbers are prime. And if a number is not prime, we call them composite numbers, right? Composite numbers. Now, so the integer 7 is prime because its only positive factors are 1 and 7. But 9 is composite because it's divisible by 3. what do we mean by factors? For example, any prime number we should be able to write it 7 is equal to 1 times 7. 2 is equal to 1 times 2. And 3 is equal to 1 times 3. 5 is equal to 1 times 5. So if a number is factor of 1 in itself, is a prime, as you see. Here, every positive integer greater than 1 can be written uniquely as a prime or as the product of 2 or more primes, where the prime factors are written in order of non-decreasing size. This is very interesting thing that if a number is prime, that means that number it's divisible by 1 and itself only. So we can write them only in the form of the 1 times itself. That's the factor. Now, if a number is composite, meaning it is divisible by more number than just 1 and itself, then we should be able to write that number in the product in terms of the product of prime numbers. All right? For example, 4, for example, let me get to another page. For example, 4 is not a prime number, so I should be able to write them as 1 times 2 times 2, right? Which is equal to 4. 1 is a prime and 2 is a prime. So any composite number we should be able to write them in the form of product of number of prime numbers. Now, of course, this we could write them 1 times 2 to the power of 2, and also we could write them 4 is equal to the power of 2. And 2 is the number that we call them prime. This means the repetition. All right? So any non-prime number or a composite number we should be able to write them in the form of product of number of prime numbers. That will be equal to that composite number. So, for example, 100. It is divisible by 1, which we assume that. Divisible by 2, we write them down, makes them 50. Divisible by 2 again, makes them 25. 25 divisible by 5, makes them 5. And 5 is divisible by another 5. And so there are 2 2's, 2 5's, so say 2 to the power of 2 times 5 to the power of 2. So 100 is a composite number, but we could write them in a product form of prime numbers. All right? And 641 is a prime number. It's not divisible by anything. How do we know? It's not divisible by 2, since it's an odd number. It's not divisible by 3. It's not divisible by 4. It's not divisible by 5, not 6, not 7, not 8, and not 9. Therefore, it is a prime number. It's only divisible by 1 in itself. On the other hand, 999 is a composite number, and you divide them by, we see, not divisible by 2. We start from the smallest number. Then we go to 3. It's divisible by 3. You get 333. Divisible by 3. You get 111. It's divisible by 3. You get 37. So it is equal to 3 to the power of 3 times 37. 3 is a prime number and 37 is a prime number. So composite numbers always can be written as a product of the number of prime numbers. And the prime numbers are just written as they are because they are only divisible by 1 and themselves. And same thing goes to 1024. It's a composite number. You keep dividing them by 2 and comes to the 2 equal to 2 to the power of 10, right? And 2 is a prime number. Here are this is the way we find the prime numbers. And this is what I did over there. Delete all the integers other than 2 divisible by 2. Then delete all the integers other than 3 divisible by 3. Next, delete all the integers divisible by 5, by 7, and since all the remaining integers are not divisible by any of the previous integers other than 1, then the primes are. This is to find the prime numbers between 1 and 100, right? So we start with number 3 with 2, because that's the first divisible number. And 2 is a prime number. Then we go to 3. We want to find all the prime numbers between 1 and 100. That is what we are doing. So how do we do it? We start by the first number, greater than 1, right? We start with 2. 2 is a prime number. We go to 3. Is 3 prime number? Yes. We go to 4. If we want to find out if 4 is a prime number. Well, it is divisible by 2, so it's not a prime number. We go to 5, and 5 is not, it is divisible by 5, and we leave him there. And then we go to 6, we go to 7, and we find out all the numbers that are not, that are prime. This solution misses the 5, so the 5 also is a prime numbers. The solution misses that one. And it is probably dropped at the print times, but that should be there, that 5 has to be, is a prime number. And another way of finding the prime numbers between any certain number, between 1 and, let's say, 222, or 1 and 250, or 1 and 260, easiest way to do it is, there's a theorem that we say, for example, if I want to find the prime numbers for well, let me pick a number that makes easy. For example, I say, what is the prime number between 1 and, what are the prime numbers between 1 and 110? All right. Or I want to say, let's take a look at here. If an integer n is a composite integer, then it has a prime divisor less than or equal to square root of n. All right. Now, I want to find basically to see what are those numbers. You take the square root of 10, and let's say 110. Let me calculate that one. 110, it comes to 10.48 about, so it's 10.48. All right, so that means the product, if I want to find out if it's 110, if it is a composite number, what are the products here that I can place in here and give me those numbers? And so it should be prime numbers between 2 and 10, since it has to be less than 1048, so between 2 and 9. All right, so it has to be numbers between 2 and 9, so I can write them in this format. If I want any composite number, we said it can be written in the form of multiplication or product of the prime numbers. In that case, how do I find that? Let's take the square root of 110, for example. It is 1048. Then I say 110 is equal to product of number of numbers, number of the primes that are less than 10. And so, for example, let me see if here it didn't do it. And let me see if I have this example someplace that I can write it down for you. Well, I'll have another example. For example, 101. All right. In 101, I want to find out what is it that it is product of what numbers it is. And if n is a composite integer, then n has a prime divisor less than or equal to the square root of 10, the square root of itself. And let's say number is 101. Then the square root of 101 is equal to number square root of, let's calculate that, 101, it is equal to 10.04, almost. All right, so the numbers has to be less than 10, so 101 is equal to, basically, is going to be equal to a number that it is 2 times, 3 times, and we calculate all the prime numbers, that comes to equal to 101. And that is the answer. For example, let's get to another example. What's the factorization of 7007? All right, 7007, and the way you do it, you always you try to multiply. First, you calculate what is the square root of 7007, and that would be 7007. That would be 83.70, 83.70, and then we start dividing it by all prime numbers, and to see how we can factorize 7007. And we start with 2, it's not divisible, and 3 is not divisible, and 5 is not divisible. And however, 7 divides 7007. 7007 is divisible by 7, so we say 7007 divided by 7, and that comes to 1001. And then we start dividing 1007 with other prime numbers. Now, we started here by 7, so we start dividing 1007 by 9. We go on with that, with the number greater than 7. All the way we came to the 7, and then we start dividing that 1007, 1001. We notice that 1001 is divisible again by 7, and that gives me 143. And then I go back to the 8, 9, and I notice that 143 is divisible by 11. And I'm moving on along with the prime numbers, and that gives me 13, and 13 is a prime number. So I say 7007 is equal to 7 times 1001, which I got them from here, and which is equal to 7 times 7. 1001 is also divided by 7, and by 143, and then I say that's equal to 7 times 7 times 143 is divided by 11, and which just gave me 13. So if you multiply 7 by 11 by 13, every one of them are prime numbers, right? And then we say, okay, 7007 is factorization of this one. Because we said every composite number is product of the bunch of prime numbers, right? That was the concept that we discussed. Now, there are infinitely many primes. That we know, and I don't want to go through the proof. Proof is very famous, this proof, in mathematics for the mathematicians, but not for us. But there are infinitely many primes. That means we have unlimited prime numbers. And interestingly, we only know up to a certain number. We don't know every one of them. And that was by the help of the computers that we have been able to calculate with all the way to 13-digit numbers, that what are the prime numbers, that they're not divisible by anything except the one and it themselves. And also here's the Mersenne primes. These are also famous. Prime numbers of the form 2 to the power of p minus 1, where p is a prime, are called Mersenne primes. For example, 2 to the power of 2 minus 1 is equal to 3. All right? And these numbers, like 3, is called Mersenne because have the form that are 2 to the power of a number, then minus 1 is equal to that number. 2 to the power of 3 minus 1 is 7. 2 to the power of 5 minus 1 is 37. 2 to the power of 7 minus 1 is 127. All are Mersenne numbers. And however, there are some, for example, 2 to the power of 11 minus 1 is 2047. It's not a Mersenne prime, since 2 to the 2047 is equal to 23 times 89. All right? It's equal to 23 times 89, and those numbers are special numbers because there are regular Mersenne numbers. So the Mersenne numbers are the ones that they qualify to be in this form, meaning, for example, 3 in Mersenne number, Mersenne prime, since we can write them 2 to the power of 2 minus 1 is equal to 3, or 7 is a Mersenne because I can write it that way. And now the 23 and 89 are not that, well, 23 is a prime number because, you know, we calculated the, let's look at these prime numbers. 23 is here, 89 is here, as you see that. So 23 and 89 are prime numbers, however, do not come up with this format, so we don't consider them as a Mersenne prime number. Now, there is an efficient test for determining if 2 to the power of p minus 1 is prime, and the largest known prime numbers are Mersenne primes. As of mid-2011, for these 47 Mersenne primes were known. The largest is 2 to the power of 43 million 1 minus 1, which has nearly 13 million decimal digits. These all are used in special applications, as I said, in computer science, and the reason we are discussing it here because you need to know what is Mersenne primes if in case you get to study any upper level securities, encryption, decryption, and cryptology, on any of those, then you need to be able to understand what those numbers are. And as you see, we only know up to the limit that we know. There are only 47 Mersenne prime numbers in the whole, as far as we know. We know there may be more numbers than that, but so far we have been able to calculate this much. Distribution of the primes, and this is something that I'm just going to mention it briefly. Mathematicians have been interested in distribution of prime numbers among the positive integers. In the 19th century, the prime number theorem was proved, which gives an asymptotic estimate of the numbers of primes not exceeding x. For example, you have a number, let's say 100. You want to know how many primes we have less than that one. And usually we say the theorem tells us that the number of primes not exceeding x, for example, can be approximated by x divided by natural log of x. And that's all we need to know. And I'm going to pass those. Greatest common divisors. When you study the chapter, this section 4.3, only please pay attention to the sections that I'm covering here. Read all of them, but pay attention to this. For example, we want to find out what's the greatest common divisor. Let a and b be integers, all right? Not both 0. The largest integer, d, such that d is divisible by a, and also d is divisible by b, is called the greatest common divisor of a and b. The greatest common divisor of a and b is denoted by GCD of AB, GCD of AB. We want to know what is the greatest number that both a and b, if I have two numbers, a and b, I want to know what's the greatest number that both a and b are divisible by that number. And I'll call that one greatest common divisor. And sometimes I want to find out what's the least divisible number by both of those decides, and that's called LCD A and B. So we'll look at both of them. We can find the small numbers by inspections. Very simple. But the largest number, it's going to be an issue, which I want to show it to you. How about, let's say, look at for the smallest number. Small numbers. Let's say, what's the greatest common divisor of 24 and 36? That we can do it by inspection. For example, 24 and 26 is 12, because after 12, none of those numbers are divisible by any number. But they both are divisible by 2, and I believe by 2, and then it jumps to the 12. There is no other number, and the 12 is the greatest number. Or what is the greatest common divisor of 17 and 22? 1 is the greatest number, because they both are, well, 17 is a prime number, 22 is not a prime number, but 17 is only divisible by 1 in itself. So 22, if it's not divisible by 17, then forget it. The greatest common divisor would be 1. And the integers a and b are relatively prime if their greatest common divisor is 1. If we have two integers, we want to find out GCD, their greatest common divisor. If their greatest common divisor is 1, that we call those numbers relatively prime. Usually one of them is prime and the other one is a composite number. All right, that's the situation. So we say, here's the example. Determine whether the integers 10, 17, and 21 are pairwise relatively prime. Well, GCD of 10 and 17 is 1. GCD of 10 and 21 is 1, because 10 is 21. You cannot find any number greater than 1 that 10 and 21 are divisible. 17 and 21 also is 1. Therefore, we say 10, 17, and 21 are pairwise relatively prime. And how about 10, 19, and 24? We do the same thing. And 10 and 24 is, their greatest number is 2. All right? And so 10 and 19 and 24 are not pairwise relatively prime, because look at it, 10 and 24, the greatest the common divisor is 2. And it's not 1. If it is 1, we say they are relatively prime. And here's some more of an example of these. All right, how do we find it? How do we find the greatest common divisors using prime factorization? Remember we said all composite numbers can be written as a product of prime numbers. And now we want to use that concept and find the greatest common divisor of any two numbers. And suppose the prime factorization of a and b are a is equal to p1 to the power of a1, p2 to the power of a2, all the way p sub n to the power of a sub n, and b is equal to p1 to the power of b1, p2 to the power of b2, and all the way, where each exponent is a non-negative integer, and where all primes occurring in either prime factorization are included in both. Then what we do here, we say, we write this one down, because then it would make sense. We're going to do one example, and well, before I do the example, let's take a look at here. We have a and b. We write this first digits, first factorization element here and here that are same, p1 and p1, and then we write the minimum of a1 or b1, p2 minimum of a2 and b2, all the way times p sub n, minimum of an and bn, all right? And then we pick the minimum and we write the numbers. Let's look at the example. And example is 120 and 500. $120 and 500. All right. I want to find out the greatest. Let's say this is A, and this is A, and this is B, right? We want to find the GCD, or the greatest common divisor of A and B. And we said that is equal to P1 to the power of minimum of A1, B1, multiplied by P2 to the minimum power of minimum of this A1 and B1, and then A2, B2, and so forth. All right? So the very first thing that I do in these situations, first I write them in the form that we said A has the form of P1 to the power of A1, P2 to the power of A2 times P sub n to the power of A sub n. And we said B is equal to P1 to the power of B1, P2 to the power of B2, P sub n to the power of B sub n. And I want to put them in this format, right? So first I put the A and B in this format. So A is 120, and I divide 120 by 2, and then 60, divide them again by 2, another 30, then dividing by 2, it's 15. 15 divided by 3 is 5. So it is 2 to the power of 3 times 3 times 5. And 500 is equal to 2 to the power of 2 times 5 to the power of 3. You notice that all bases are primes. All right? So now I want to find out greatest common divisor of 120 and 50. And I apply this formula. So greatest common divisor of 120 and 500 is equal to P1 here is the 2, minimum of 3 and 2, because here is the power 3 and here's power 2, multiplied by P2, it's 3, and minimum of power here is 1, power here is 0, because it is to the power of 0 that becomes 1 and it doesn't show up, times 5 is your P3, 5 to the power of, to the minimum of 1 and 3. So this is equal to 2 to the power of minimum of 3 and 2, which is 2, times 3 to the power of minimum of 0 and 1, which is 0, times 5 to the power of 1 and minimum of 1 and 3. Minimum of 1 and 3 is 1. All right? So this becomes equal to 4 times 3 to the power of 0 is 1 times, this is 5, and it is 20. So greatest common divisor of 120 and 500 is 20. That is what the problem is explaining here. And it's very usable when you want to find a common divisor. This is how the greatest common divisor, this is how you find it if the numbers are big. Small numbers, we can find them by inspection, but the large numbers, you have to follow the rules. And let me see, least common multiple, and this is also, let me see if I didn't pass anything. No, here's the least common multiple, meaning the smallest number that's divisible. It's exactly the same situation, except when you write them, you pick the maximum of, instead of minimum, you pick the maximum of those powers. P1, A1, B1, right? P1, maximum of A1 and B1, times P2, the maximum power of A2 and B2, and all the way to the end. And then you find the numbers, and what's the least significant, I mean, not significant, the least number that both of those numbers are divisible. And this is and you can find it easily in any examples that I don't want to now take your time. But for example, let me do this one. He said there are two numbers. One of them is written in this format: 2 to the power of 3, 3 to the power of 5, 7 to the power of 2, and then 2 to the 4 multiplied by 3.3. So 2 as a P1, the maximum of 3 and 4, then 3 maximum of 5 and 3, and 7 maximum of 2 and 0. So 2 would be 2 to the power of 4, 3 would be to the power of 5, and 7 would be to the power of 2. You multiply this one, you get the least common multiplier of these numbers, that they both are divisible. Also, there's another theorem here that says if you have two numbers, A and B, positive integers, the greatest common divisor of those two, that multiplication of those two numbers, for example, 120 times 500, right, is equal to greatest common divisor of 520 times least common multiplier of them, of A and B. And you can see that it works. All right, here's another algorithm that I'd like to show you. Find, this says the The algorithm is an efficient method for computing the greatest common divisor of two integers. It is based on the idea that greatest common divisor A and B is equal to greatest common divisor of A and C when A is greater than B and C is the remainder when A is divided by B. For example, the best thing is to do the example of this one, because this is very efficient way to find the greatest common divisor. For example, here's the number is 287 and 91. We want to find out. Let me go to document, right? We want to find out GCD of 91 and 287. What we do here, the algorithm says, first you take the largest one of those, 287, say equal, you divide it by the smaller number, and 91 multiplied by the quotient, that when you divide 287 by 91 is 33. There are 3 91s in 287, plus there's a remainder. You write the remainder there, plus that, all right? And then you take the 91 and you divide it by the remainder, right? 14, and that becomes 6 times 14, and remainder is 7. And of course, this is true. 6 times 14 plus 7 is 91, right? And then you take 14 and you divide them by the remainder, 7, and it becomes 2 plus 0. Once you get 0, you stop. Once you get 0, you stop. And then you say, all right, the greatest common divisor of 91 and 287 is equal to 7. Right? That's a very efficient way to calculate greatest common divisor of a number. And here it is, 287 divided by 91. Quotient is 3, remainder is 14. And then you take the 91 here, you divide them by the remainder. Quotient is 6, remainder is 7. And then you bring the 14 here and 7 here. You divide 14 by 7. It's 2, quotient. Remainder is 0. And this is the stopping condition. So you say greatest common divisor of 287 and 91 is 7. Right? It's very simple. And here is some the algorithm that you could use them and write that down. All right. I am done with this section and finding the GCD as linear. These, you can take a look at them, but I'm not going to ask any questions regarding these parts because it is beyond the scope of what we are trying to do. So I will stop at this point, and our next topic that we are going to discuss, well, I will see, and I will see you in next class, and we are going to move on to the next chapter. All right, see you then.